Hello guys, so welcome to another VHDL lesson. So we're gonna continue with our combinational circuit logic design. So, and maybe last week we or we studied the 4-bit binary subtractor. It was just a binary adder with some modification for the input, especially the second, number that you wanna subtract basically, and also the carry. So basically, we said that we can convert the subtraction operation into an addition operation if the subtracted number, I mean, if you say a minus b, then this minus b, if we represent b as with its two's complement, we can just add a to the two's complement, and this will be just equivalent to the subtraction operation. Okay, two's complement is basically b bar plus 1. So basically what we did is that we use the same architecture of the binary adder, which is for 4-bit subtraction. It will be for 4-bit addition. It will be 4 full adders, where each full adder takes two bits of the two inputs, 1 bit from each, and a carry. Okay, so basically, B, instead of just inserting B into the full adder, we're gonna just insert the complement of B. So basically now the binary adder takes B bar. And we said that the two's complement is B bar plus 1. Where is the 1? Is basically the carry bit here. So you remember, guys, first stage, the first full adder, which adds the least significant bits of the two binary numbers, takes a carry of 0 in the addition, but here in subtraction we'll make it 1, so that it's like if we are adding a plus b complement plus 1, and the b complement plus 1 is just the two's complement of b. That's basically the subtraction operation. Now, how are we gonna do that in VHDL? It will be something extremely similar, and I'm repeating this because again, this is the idea of having a hierarchical, or structure, design. Uh, Most of our designs will be a mix. Some you're gonna define some package and insert it in your code and put some other codes that uh, describe something, describe some behavior in your design. Okay, so in that code here, I do both. I uh, uh, i use the full other design that I have before, the package that we talked about many times. Okay, and we used it when implemented the binary other, and also I made some behavioral coding to implement the b bar, which is really simple thing. Okay, again, you have two ways to implement such design here. You can just, here you have 4 full others, so you can just have these 4 lines here, which I commented now because I'm gonna explain why. But you can just ignore this, comment this part. Let's comment this part. Just pretend they are not, this part is not there, and just use this part here. Let's uncomment it, and you can just comment a block in VHDL in model sim. Just highlight it, right click, and comment all or uncomment all. So let's describe this. So here we have 4 full others, which is good, and here is the package of the full other I created before and added to additional component. I'm just using it right now. So the first full other takes E0 and B0. Okay, I'm sorry, this should be not B, so let's not B. So basically, we can do something easier here. We can, generate node B before that. So we should have three lines like this for loop. So you just loop over B input, and store the complement of each bit in a signal, which we call Bn. So Bn is basically B complement. That's it. Okay. So Now the first full adder will take Bn of 0, which is basically B of 0 complement. The second full adder will be Bn of 1. The third full adder will be Bn of 2. The fourth full adder will be Bn of 3. Okay? You can just implement it in that way. And remember, the first full adder takes E0 and Bn of 0, or B complement of 0, not B. And the carry is 1. Okay? Then this full adder will give you an internal carry bit, which is C1. And I call this C1, C2, C3, C4 in some internal signal, which I call rebel carry. It's internal signal. Because remember, guys, subtractor has no carry output, has only sum output, which is subtraction output, basically. But we call it, usually, we call it just a sum because we are using, the same circuit as a sum. And actually, we are doing some operation here because we are adding A to B complement. So still, it's addition, but equivalent to subtraction. So the output here is just 4 bits. There is no carry. So these carry bits here are just internal signals. So I just combine all of them in this rebel carry signal, which is logic vector, standard logic vector, 4 bits. This is better than name 4 variables. It's just one line here, one word. Okay. So the second full adder, which is that guy here, will take A1 and Bn of 1. Bn of 1 is basically B of 1 complement. Then the first carry bit, rebel carry of 0. And it will give you the second carry bit, rebel carry of 1, and S1, or S of 1. Okay? The third, basically the same, just repetition, but instead of 1 will be 2. I mean A of 2, Bn of 2, or B complement of 2. And we'll take this carry here, C2, which is rebel carry of 1 in our case, and it will give you C3, which is rebel carry of 2, and S2. And the same finally for this. This will work like charm with you. Okay. Also, this is 4-bit. You can just copy and paste. If it's 8-bit, okay, you can just copy, copy these 4 lines, and modify them. It's easy as well. But 32 bits, no. 32 bits, still you can copy and paste and modify, but it will be very, very error-prone operation. I tried this many times, and I know what I'm saying. Imagine now 64 bits or 128 bits. When these 64 and 32 are 128 is regular, weights for our variables in computer architecture, for example. Okay, so I'm not just imagining. It's a practical problem that you must take care of. So that way, although it's good and working, but not efficient or not scalable, we can say not scalable. That's basically much better word to describe it. Not scalable. I mean, when you try to implement the operation for 2 input variable, binary variables that has more than 4 bits, this will be not scalable for you, not good for you to implement. But generate a statement will work like a charm in that case. So you remember, guys, we studied the generate statement, and actually we used it here. Even with that guy, we used the generate statement in here. Okay, and instead of doing 4 lines, each line will have separate bit, a complement of a separate bit. I mean, we can just replace this statement with 4 lines. The 4 line will be Bn of 0 equal to B of not B of 0, Bn of 1 equal to B not B of 1, and so on. Okay, but generate a statement, since you will generate something, then just use generate for loop and generate. So here we have 4 lines. For the first one is out of the repetition because it has this one here. Okay, so basically we're gonna make it in a separate line. That's fine. And you can even, make this rebel carry 5 bits and assign the first bit to 1. Then you will not have a separate line. You can do everything inside the generated statement. It's up to you. But since it's just one line, that's it's okay. You have both options, I mean. Okay. So this basically when we run generate here, the compiler will will generate for us 3 lines out of this line. The first line will be full adder port map a of 1 because I of 1, I is equal to 1 in the beginning. Okay, main of 1, rebel carry of 0, rebel carry of 1 is 1, and so on. Okay, that's basically what you're gonna get. I'll just here one comment because this will be so if you're gonna use the first way or the first method here. So I just forgot and just put C. And this is what I'm saying. Because these 4 lines, as I said, are just copy and paste from another design. Basically the binary other. Okay. So and I modified. In the binary other, we have here a carry. The final carry C4 is a carry for the whole circuit. Okay, so there was here in the entity there was another output which is the carry out, but we don't need this, so it will be just part of the rebel carry signal. Actually, it's bit number 3, and that's the kind of problems that you're gonna have, is that you may end up forgetting maybe one modifications that you must do, but you forget about it, and it will spoil everything if in your simulation or your design basically. Okay, so that's basically the design. Let's now compile it and see if we have any error. Looks like we don't have. Good. Now let's visit the test bench for that guy. Okay, it's really very nice test bench. So again, you have 2 inputs and the output is this. Then you define 3 signals, 2 for the input and 1 for the out. Okay, and don't mix bn here with this bn. Okay, this is just another file. You can define whatever signals. These signals, you can name them exactly with the names of the names here. There is no problem at all because this is just different files. Okay, so I just repeat the same the same name for different variables. This signal here is defining the inverter of the B input, but this is something else here. This is basically defining B itself. Okay, although it's the same name, so don't be confused. You can use basically what I'm saying. If you have 100 design in your project, you can reuse the names of the variables, no problem at all, even in the design in its test bench. Okay, good. And here is I am instantiating, my design, the subtractor, and I'm calling it here rebel carry subtractor because basically this is the rebel carry other, if you remember, guys. So it's based on the design, the rebel carry design that has this propagation or this propagated, carry, which is bad, but very simple to design again. Okay, that's why I call it rebel carry subtractor because it's basically same as the rebel carry adder. Is except of course for the inverter for the input and the carry input of 1. Now how I do the simulation here, it's really simple as well. So I make 2 for loops because we have 2 variables. Okay, you want to say the following. You want to say 0 minus 0, then 1 minus 0 and 1 minus 1, then 2 minus 0, 2 minus 1, 2 minus 2, then 3 minus 0, 3 minus 1, 3 minus 2, 3 minus 3, then 4 minus 0, 4 minus 1, 4 minus 2, 4 minus 3, 4 minus 4, and then 5, and so on until you reach 15 with the same sequence. Okay? So you want to try all the combination. So you should have 2 loops, we can say, because basically you have two inputs, A and B, one for A and another loop for B. So the I loop here is rotating or iterating from 0 to 15. Okay, and here is you wanna assign I to A. Remember, to AN is a standard logic vector. Okay, I here, in the for loop is constant. It's called the constant. It's not a signal. It's not a hardware. This is something for simulation only. Okay. So basically, this I is a constant. So to convert or to assign a constant to uh, a standard logic vector, it's not like programming language. It's easy to know. So to do that, we should define this package here, this library here called IEEE numeric standard.all. So this new library that we're gonna see we are seeing for the first time allows you to convert I, which is constant, to something, to a signal, basically something that is represent something, some signals that flow through a wire. It's a hardware. Okay. So you can just write this line in here. Okay, and put here the constant that you want to assign to the standard logic signal, and put here the name of the signaling. It's just like a template that you fill again. Okay, that's good. So basically now AN, the input A, this guy here, this A, will iterate from 0 to 15. For each value of A, you're gonna iterate B, which is now the counter G, from 0 to A. I mean, if A is 1, you wanna subtract 1 from 0 and 1 from 1. So you're gonna iterate or generate values for B, the subtractor, this, the other variable. From 0 to the value of B, just to avoid having negative subtraction, because negative subtraction here will result in a negative number. Negative number mean you will find this output here, you will find the last bit here 1. If you find the last bit 1, that means it's 2's complement of something. So you can't just read it as normal binary. You should generate it. You should. I'm sorry. You should convert it back to its original form to know which number is this. For example, if this is 4 ones, 1, 1, 1, 1, this is not 15. This is basically something very different. If you have here in the output 1, 1, 1, 1, it's not 15. If you want to know the real number, first it's a negative number. To know what it is, you should take its 2's complement. The 2's complement of 15 is just complement it will be 4 zeros, then add 1, it will be 1. 1, and it's a negative number. Then when you see here 4 ones, that means it's minus 1. Okay, so I just want to avoid these cases, just to make our output readable for us. Okay, but you can of course do it, and this circuit can do that. That's fine. But just to test with cases that we can easily read and understand, and weigh if it's wrong or right. Okay, so that's why I stop here at I, so that B all the time is less than A. So A minus B will give you something positive. That's my point. Okay, good. So this is basically the trick that I did here in this test bench. It's a new one. Okay, and let's now, I think everything is, I didn't make any changes to the system, so we can simulate. So simulate, start simulation, and we need rebel carry subtractor. R is way down. Rebel carry subtractor, test image. Okay, I don't think we need the, so let's just keep this window here. We don't need the design anymore. Okay, so here is the three variables, the two inputs and the output. Let's change it to unsigned. Okay, and we have many many more than 100 cases here. Okay, so what I'm gonna do, gonna first remove all this stuff. I'm gonna simulate with 100 steps each time. So each click here will generate 100 case of our simulated cases. So let's generate here. Let's generate another 100. Okay. Let's now check our output. Let's zoom in a little bit. Zoom out, I'm sorry. Okay. Now look, 0 minus 0 will give you 0. Now we have 1 and A. This is A. So let's change the color of this to yellow, for example. So to differentiate the input from the output. Good. Now 1 minus 0 is 1. 1 minus 1 is 0. Then A now is 2. So we'll change B from 0 to 2. So 2 minus 0 is 2. 2 minus 1 is 1. 2 minus 2 is 0. Then A becomes 3. So we're going to generate, or make B variable from 0 to 3. So 3 minus 0 is 3. 3 minus 1 is 2. 3 minus 2 is 1. 3 minus 3 is 0. And so on. So we can pick another, values. Let's check 15, for example. So if this is the last value for A. Okay, so B now will change from 0 to 15. 15 minus 0, 15. 15 minus 1 is 14. 15 minus 2 is 13. 15 minus 3 is 12. 15 minus 4 is 11. 15 minus 5 is 10. Minus 6 is 9, and so on. Okay, that's basically, the subtraction, guys. Okay, so it looks like our circuit is working, and you can do, by the way, this in. I mean, you can now try. So I will share with you guys the test, the files, all the files. Then you try this one, the default one. Then try also, this operates. Of course, comment out this first. Then uncomment this and try this, and you should get the same output as well. Okay, guys, thank you very much for watching this lesson, and see you in the next lesson. Bye bye.